The text discusses the potential dangers posed by space objects such as asteroids and comets in our solar system. It highlights the unpredictability of these objects and emphasizes their potential to cause significant damage to Earth. The historical example of the Tunguska event in 1908 and the potential catastrophic consequences of similar future events are also presented. Additionally, the text mentions the York cloud as a source of comets and describes the threat posed by near-Earth objects, NEOs. It concludes by underscoring the importance of monitoring and potentially mitigating the risks associated with cosmic debris. To summarize, the text emphasizes the potential dangers of space objects, particularly asteroids, and the importance of monitoring and addressing the risks they pose to Earth. Of Chile in Mexico, with a force of 100 million megatons of TNT. Here we see Earth hurling billions of tons of its crust into space, creating a blanket that blocks out sunlight, destroying the food web at its roots, and killing off countless species. The ferocious impact is thought to have been a factor in the extinction of the dinosaurs. We can think of asteroids as being bad things, but if it were not for an asteroid, we wouldn't be here today. Our mammal ancestors were running on their foot, trying to avoid being appetizer for T-Rex. T-Rex gets taken out. Well, this opened up an ecological niche that allowed our mammal ancestors to evolve to something more ambitious, that are root and outcomes the primates, and among the primates, we have people. But it's strange that the same kind of cosmic boulder that made it possible for humans to live could one day wipe us out. In 1998, Congress asked NASA to find all near-Earth objects that were at least half a mile across, and what they found was unsettling. There are more than 850 NEOs near our vicinity. These asteroids are our nearest and most dangerous space friends. Finding these near-Earth objects is a bit like keeping an eye on storms. As you watch it day after day, you get a better idea of its path and can figure out where it's going, how big it is, and how fast it would hit the Earth if it did. By using telescopic technologies, NASA's Space Guard survey has detected over 90% of all near-Earth objects deemed harmful. These scary things could hit Earth with more power than all of the nuclear weapons in the world right now. Such an impact could trigger mass extinction. We wouldn't expect one to hit every few hundred thousands or millions of years, but if one did, it could wipe out different parts of the population. So there are events that happen very rarely but have big effects when they do. If they hit Earth, they would have impacts all over the world. They would not only wipe out a continent with very strong shock waves, but the debris would also be thrown into the air and land all over the planet, heating the air to 1,000 degrees and all the vegetation all over the world where that happens would flash into flame. Smaller objects could also cause disasters. So Congress has asked NASA to find all NEOs with a diameter of 500 feet, which is as big as the Colosseum in Rome. A big object like that could wipe out a city or even a small state. Scientists are most worried about the asteroids they haven't found yet, not the ones they have found. Well, at the moment, there are about 2,000 objects that we can't say for sure won't hit Earth. We now have the technology to keep near-Earth objects from ever hitting Earth again. We can now literally start to change the local solar system to make it better for our music life. The question is whether or not we will end up like the dinosaurs. It's hard to believe that the Earth has been around for more than 4.5 billion years because it's been through a lot since it was born. Asteroids that come into our orbit every year keep hitting our world like a boxer. But one day, Earth could be knocked out. We've learned that near-Earth objects fly by us all the time, and we're getting more and more able to change our surroundings to help us stay alive. A rock in space named Apis in 2004, this pockmarked rock about 750 feet across, came close to Earth. Now it's scheduled to pass dangerously close to our planet again on Friday. In 2029, the asteroid Apis will pass by the Earth at an incredibly close distance, visible to the naked eye. Although there's a 99% chance that it will miss the Earth, there is a small 1 in 45,000 chance that it could hit in 2036 after passing through a gravitational keyhole. Scientists have proposed potential impact sites, particularly concerning the Pacific Ocean near California, which could result in devastating tsunamis. Efforts are underway to develop strategies to deflect or change the path of such asteroids, including potential international collaboration and the use of space probes or even manned missions. Public awareness and preparedness for such potential threats, including training in disaster and emergency management. Additionally, amateur astronomers can contribute their efforts to assist in identifying and tracking potential hazards from space. Smaller and potentially destructive asteroids are hidden in the universe. So would you like to be an amateur astronomer? Who knows, maybe you can be one of the guardians of our home. In far-off galaxies, galactic invaders are at work. 3 times daily, a strange flash pulsates across our sky. It is hundreds of times stronger than all of the world's nuclear weapons put together, but it wasn't made by people. And if one happens close enough to Earth, it could wipe out all life there. Most people on Earth don't know about the possible dangers in space. Imagine this. A huge star explodes in our galaxy, the Milky Way, sending a deadly burst of energy hurtling toward our planet. This is a gamma-ray burst, which is the biggest blast since the Big Bang. There are no signs that something bad is about to happen, and then it strikes. The radiation that is pumped up heats up the high atmosphere. Our layer of ozone heats up across the atmosphere. Human beings burn to death from radiation, 100 times the fatal dose. When the ozone layer gets thinner, temperatures rise all over the world. This makes storms, tsunamis, and hurricanes happen. Most life on the surfaces of land and water incinerates. This may sound like science fiction, but if a gamma-ray burst from 100 light-years away hit Earth, it could happen. Gamma-ray bursts are the most bright blasts in the universe. They must have a huge amount of power because they're so far away and yet still so bright, as much energy as the sun will give off in its full 10 billion year life. We know there are many planets and many stars in the universe, so gamma-ray burst could have wiped out a lot of different cultures. In the 1960s, this strange blast of radiation was first seen. At first, because these gamma-ray bursts are so bright, most scientists thought they came from our own galaxy, the Milky Way. There are a few reasons for that. One of them is that if they are outside the galaxy, the energy is almost too much to believe. But back then, even the most powerful telescopes couldn't figure out where they were or how far away they were, because the burst only lasted a few seconds and then went away. But then scientists started to wonder about their afterglow. Most blasts in space leave a glowing trail behind that can last for days or even weeks. In the late 1990s, satellites with better optics and X-ray monitors were finally able to catch the afterglow of a gamma-ray burst. It became clear that gamma-ray bursts actually came from outside our galaxy, millions and billions of light-years away, so their power had to be really out of this world. The brightness of the gamma-ray burst is the same as that of 1,000,000 trillion suns. This huge explosion could wipe out all life on Earth. But why do they happen? We are very sure that a common gamma-ray burst is caused by the death of a star that is at least 10 times the mass of the Sun, and these kinds of stars aren't very common. When a very big star dies, it falls apart and forms a black hole. Black holes are made when a mass of matter shrinks to a point where it is so dense that light can't get out. But experts think that some of the star resists getting sucked into the center of the black hole. As a result, a high-speed spinning disk of matter forms around it. In a matter of seconds, plasma jets shoot out from the poles where it spins. These beams of energy unleash dangerous gamma rays into space. At the same time, the gamma ray bursts are rejected, the collapsing star explodes or goes supernova. To the extreme, gamma ray bursts are so bright because they take a huge amount of power and focus it on a very small area of the sky. Only one of every 300 gamma ray bursts is directed toward us, so we only see one of those 300. Even if a gamma ray burst happened not 100 but 1,000 light years away, the Earth could still be destroyed in a way that is similar to the end of the world. If a gamma ray burst happens within 100 light years off the Earth, then it would be approximately 500 times brighter than the Sun and made in gamma rays. The energy sent to the high atmosphere of Earth would be the same as if 100,000 megatons of nuclear bombs went off. The ozone would be depleted, and we'd have acid rain. But we'd also have flash burns, incineration of vegetation, perhaps something resembling nuclear weather, so many species could go extinct all over the world. Now, the other side of the Earth would be a special place to be because gamma rays don't go through the Earth. The repercussions of altering the atmospheric composition and ozone depletion would ultimately come to the other side, and there, nobody knows what will happen. This nightmare scenario has a 1 in a trillion probability of occurring. Once in Earth's history, it's going to be a nasty day if you get caught in the beam. For the reason that this is extremely powerful radiation, you don't want to be in the vicinity of this sort of energy, since it has the potential to break down your own molecules. Currently, there is no way to protect humanity against gamma-ray bursts that occur in close proximity to Earth. They move at the rate of 186,000 meters per second, or the speed of light. By the time we detected them, they would have already struck our planet. Gamma rays bursts could pose a hazard to the Earth or to anything living that came within their born sight. Astronomers think that gamma ray bursts could be the cause of some mass extinctions on Earth. The one that happened 450 million years ago and killed off the Ordovician and Saloon species was probably the worst. Creatures that lived near the surface of the ocean were hit much harder than those that lived deep in the ocean. This is consistent with what would. During a strong gamma ray burst in a galaxy the size of the Milky Way, gamma ray bursts happen about once every few hundred years, according to astronomers. Even though they can be very bad, you have to be pretty close to be hurt by one. A gamma ray burst happens about once every 5 million years, which is close enough to affect life on Earth. In other words, since the Earth was made 4.6 billion years ago, there have been about 1,000 events. So the chances of a close gamma ray burst are at 0. But they're low enough that you don't need to worry about them unless you want to live for about 5 million years. Humanity obviously made it through the gamma ray explosion unharmed, but this still demonstrates how far their effects may travel. Don't fret. Threats to Earth from gamma ray bursts are extremely low. All of the closest contenders for gamma ray bursts have been studied by astronomers, and none of them are either close enough or oriented in a way that would cause them to strike Earth. Therefore, what do you think? The Sun has been a friend to Earth for more than 4 billion years, warming and feeding it. Sadly, the thing that gives us life will probably be what kills our planet in the end. The Sun and the Earth are connected in a special way. The Earth is a certain size, has life on it, and has seas, and these things are all affected by the Sun. The Sun is the reason why there is life on Earth, and it will also be the reason why it will end. When our solar mother really turns up the heat, Earth's bond with the Sun will start to break down, because it burns hydrogen into helium. The Sun gets hotter. One helium atom is made up of 4 hydrogen atoms. That means that there are bits of fuel moving around inside the Sun, and because of this process, the Sun has to get hotter and brighter to stay up. As the core of the Sun gets hotter, the upper part will get bigger and turn red. When you build a campfire, you put a lot of wood in it. When enough logs are burned, the whole thing falls down, sending out a huge burst of sparks and making the fire much brighter. In a way, because the Sun is currently burning hydrogen into helium, you could say that helium is the ash of that process, and then as the Sun collapses enough, the ash relights and the helium burns into carbon, and then things really heat up. At this point, the Sun will grow bigger and bigger until it becomes a red giant and burns up most complicated life on Earth. When the Sun turns into a red giant, it will grow to be 30 times bigger than it is now. This means that the Sun's surface will be beyond Mercury's orbit. The Sun will shine brighter by about 1,000 times. That's going to make the Earth so hot that the outer crust, the rocks, the soil, part of the Earth will melt. The whole planet would be a ball of glowing fire. The Sun will cook the planets closer to it, and even though it will turn red and get cooler, the Earth will get much hotter, just leaving the Earth a burnt cinder like a charcoal briquette. So that would be bad for all life on Earth, and it's not clear what will happen to the Earth as a red giant. The Sun's size will change before it collapses to become a white dwarf. The Sun will become a sun that's very small and extremely dense, only about the size of the Earth. It will sit down there at the center of our solar system, very much fainter than it used to be. Then everything starts to cool down, and since that object is no longer making energy, it too starts to cool down. The last thing that will happen to the solar system is that it will cool down and freeze before the sun turns Earth into a snowball. People will probably move to another world or die out, but the sun could dry up our world a lot faster. If the sun doesn't kill us during the red giant phase, it could kill us sooner if it gets bright enough to dry up the seas. Water is an important part of life, so if the Earth loses all of its water, that's another reason why life might go extinct, and it would again be the sun's fault. There might be ways for Earth to get more time. As the sun gets bigger, it also starts to lose mass much faster than it does now. And of course, if it's getting less massive, it has less of a hold on the Earth. The Earth's orbit will get bigger as it moves farther away, so it's kind of a race between the growing sun and the rising heat from the sun and the Earth, which is actually moving away from that fire that's getting too hot. Even if our world doesn't get cooked or frozen by the sun, its future looks more and more bleak. In the far future, the Earth and the rest of the universe may have to deal with the biggest monster in the cosmos. No one thinks that the most dangerous enemy of Earth is hiding among the stars. The dark bad guy will tear the universe apart. Even galaxies will break apart. The stars and planets will fall apart. The Big Rip is the name given to the end of the world. When it starts, it won't stop until all of the atoms and nuclei in the universe aren't chopped up. The Big Rip is really the end of everything, a sad idea about what will happen to the universe in the end. We used to think that the universe, which is currently expanding, can reach a point of maximum expansion. The idea behind the Big Rip is that the growth will not only keep going and speed up, but will also tear everything apart as it goes. And there is something like a vacuum pulling everything outward. This strange thing called dark energy might be to blame. Probably the most important thing for cosmologists to do right now is to figure out what dark energy is. Dark energy is called dark because you can't see it. We can tell what it is because of the way it changes the way the universe's gravity works. You can only start to see the effects of dark energy when you look at its qualities on cosmological length scales that are billions of light years long. It causes things to be pushed farther away from each other and contributes to the expansion of the universe. In the 1920s, Edwin Hubble, after whom the Hubble telescope is called, was the first person to notice that the universe is getting bigger. But it wasn't until 1998 that a top team of scientists measured that this growth is speeding up like a train out of control. As the universe gets bigger, every other galaxy moves away from us. In normal growth, the size of each galaxy stays the same. But if the universe is expanding very quickly, then each galaxy can also grow. Scientists say that the Big Rip is the end of the universe. They have even made a countdown to the end of the world. 1 billion years to pull apart clusters of galaxies, then hundreds of millions of years to pull apart galaxies themselves, and then to get to the size of the solar system. We're talking about hundreds of thousands of years. Then it will take less than an hour to tear the Earth apart. It's kind of cool to imagine what that would look like if we were in a protective capsule watching things happen. We would see the swallow of darkness that starts coming towards us. At that point, we would no longer be able to see any stars. The Earth's layers would be peeled off and thrown away one by one. Everything in us, including the molecules that hold us together, would be torn apart, and every atom that makes up your body would fly away to infinity within a very short time. Fortunately, mankind doesn't need to lose sleep over the Big Rip. Scientists think it will reach its peak in 50 billion years when the universe will be over 3 times as old as it is now. It's a lot of fun for us to try to figure out if this is really going to happen, to imagine what might happen in a science fiction way, and to think about what might happen to us. Are there real dangers in deep space? Tomorrow the sun could hurt us, others in the far future. But one thing is certain, something will terminate Earth and probably the entire universe once and for all. It's only a matter of time. It's useful to sometimes think about how fragile our life is here on Earth, that maybe we won't be here for all of time. Maybe there's a hope. But the way it looks, in early September 1859, people all over America could see the aurora. It was blood red and so bright that when miners in the Rockies came out of their tunnels, they thought the sun was coming up. So bright, in fact, that even at midnight, you could read a newspaper. It didn't just happen in the U.S. People all over the world saw these auroras. No one knew why they had happened, but earlier that same day, an astronomer had seen something on the sun's surface that he called a white light flare. Back then, the flare and the aurora seemed to have nothing to do with each other, but we now know that the spectacular aurora was caused by that flare, which was a coronal mass ejection. And if this violent event happens again, it could destroy our modern technological world. The sun is the most familiar thing in the sky. It gives all life on Earth heat and light. It is so big that it's hard to imagine, and it makes up 99% of the mass of the solar system. This nearly perfect sphere has a diameter of 1.4 million km and was made by the burning of hydrogen and helium for the last 5 billion years. But from an astronomical point of view, it's nothing special. Main sequence star, also known as a yellow dwarf, but looks don't always tell the whole story. Solar flares and explosions of plasma particles and radiation from its surface travel far into space. We call this process the solar wind. Solar storms, on the other hand, are very violent eruptions, and a coronal mass ejection, or CME, is the most dangerous because it has the potential to bring our high-tech society to its knees. Today, we'll find out how bad a CME could be and what astronomers are doing to keep an eye on our star to try to predict when they might happen. Step back in time to 1859, first in Victorian Britain. It was okay for a gentleman to be interested in solar astronomy, and one man did it in a very good way, Carrington Richard Christopher. We don't know what he looked like, though, because there are no known portraits of him. Carrington learned many important things from what he saw. He saw that different latitudes rotated at slightly different speeds, which meant the sun wasn't a solid body but a fluid one. But he also saw that sunspots could be the start of a solar storm. On Thursday, September 1, 1859, there were no clouds in the sky. In the morning, so Carrington was doing what he always did, which was to look for sunspots. He was using his telescope to project an image onto a screen. At 11:18, he saw two brilliant beads of blending white light appear in what Carrington calls a kind of conflagration. Stranger still, they were gone after 5 minutes for no clear reason. Carrington had seen a coronal mass ejection, which was a huge magnetic explosion, a huge cloud of charged particles that are thrown off the sun's surface. After 18 hours, the Earth was hit by an electromagnetic storm. People started calling it the Carrington event. At the time, everyone was talking about the beautiful aurora, which could be seen all over the world. Even though a few telegraph systems went a little crazy because of power surges, it didn't have much of an effect on everyday life. Don't forget, though, that this was 20 years before the light bulb was made. That was in the past. Things would be very different right now. Coronal mass ejections are common, but they can be different sizes and move in different directions. So the question is, what are the chances that something like what happened in Carrington will happen today? And how would it change things? So what is going on at the sun? On the surface of the sun, when we talk about the solar wind and space weather, the sun is made of magnetic fluid, and when that magnetic fluid rotates, it twists and distorts the magnetic field. A twisted magnetic field stores energy, which can lead to eruptions, which are called mass ejections, and these explosions are huge, sending out 1 billion tons of material at 1 million. So we want to know where these things are going, because if they move toward Earth, they could affect the technologies we use. There's a very famous event in Quebec in 1989 where some power systems were disrupted for many hours. In October, we've heard about the Carrington event, which happened in the 1800s. What would happen if it happened today, and how would it affect us? We use satellites for GPS, communication, weather monitoring, and more. However, our reliance on bigger power grids and wireless technology raises concerns about how they might be affected by solar events like the Carrington event. In 2012, a significant solar event occurred, demonstrating that such events can still happen. Predicting solar activity for the future is crucial, and efforts are underway to develop the capability to predict the size, speed, and significant risk, similar in severity to a flu pandemic, and efforts are being made to improve spacecraft resilience to extreme space conditions. Both NASA and ESA are planning to launch satellites closer to the Sun than ever before, and the UK's Met Office Space Weather Operations Centre, established in 2014, plays a key role in monitoring space weather. One of only 3 places in the world that can predict the Sun's effects on Earth around the clock. So far, the Sun has had almost no sunspots, and the side facing Earth is not expected to have any more sunspots or important CMAs. Luckily, there isn't much going on right now, and things don't look too different in the long run. So spacecraft, satellites, and power supplies should be safe for the foreseeable future. The trouble is, the foreseeable future in space weather forecasting is at most just a few days. We still don't know a lot about CMAs, like where they're going, how big they are, or when they might happen in the future. 2 new solar probes will get closer to the Sun than any other spacecraft has ever done. The Parker Solar Probe was supposed to be sent into space, and its destination will be close enough to the Sun's surface to fly through the source of the most energetic solar particles. The Parker Solar Probe is an exploration mission that will measure the gas and magnetic field near the Sun to figure out why this stuff is spreading out into the rest of the solar system. The solar orbiter from ESA might find out how sunspots, flares, and coronal mass ejections on the Sun's surface are related to the solar wind. Solar orbiter's success will be very important for our understanding of how the Sun works. We think that the Sun's magnetic field is made in a way similar to how Earth's is, but it is much more dynamic and changes all the time. We have an 11-year sunspot cycle, during which the Sun's magnetic fields move towards the poles and the polarity changes. On top of that, the magnetic field goes out into the solar system and flows over all of the planets. Solar Orbiter will measure these magnetic fields for the first time and will also give us the chance to watch the magnetic fields move to the Sun's poles. To do this, Solar Orbiter will take pictures of the Sun's atmosphere and measure the number, speed, and temperature of the particles moving across the space between the Sun and Earth. The magnetometer, which is made to measure the tiny magnetic fields in space carried by the solar wind, could be one of the most important and sensitive instruments. The Sun is ever present in our lives. It gives us light, warmth, and even life itself. For Richard Carrington, who was the first person to record a CME, it was just a strange event. But now we know that these things can do a lot of damage to the world we live in. With new satellites and more observations, we might be able to learn more about these events and predict when the next coronal mass ejection will happen. Nothing existed at the outset. After then, the cosmos began to take shape some 13.7 billion years ago. How this came to be, or if there was ever a time before time, is still a mystery. Yet physicists have pieced together an approximate timeline of significant events in the cosmos' existence using telescope data and models of particle physics. From its beginning to its inevitable demise, we examine key points in the evolution of our universe here. Welcome to the Endless Universe. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. The Big Bang is a moment in time, not a location in space. From when all else unfolded, to be more precise, it's the first second of time, the point in history from which all other seconds have been measured. The Big Bang, despite its common name, was not an explosion, but rather a time when the universe was incredibly hot and dense before space began to expand outward in all directions simultaneously. The Big Bang scenario suggests that the universe was an infinitesimally small point of infinite density. However, this is merely a convenient way of expressing that we don't know for sure what happened at that time. We now understand the cosmos to break down at the Big Bang because mathematical infinities don't make sense in physics equations. Cosmic inflation era. The next cosmic phenomenon was to rapidly expand in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but it has gained favor among cosmologists as a possible explanation for the striking similarity expansion and light from the early cosmos were reported in 2014. Nevertheless, further investigation revealed that the true culprit was nothing more than interplanetary dust causing interference. Quark gluon plasma. The temperature of the early cosmos was between 7 trillion and 10 trillion degrees Fahrenheit or 4 trillion and 6 trillion degrees Celsius, just a few milliseconds after the Big Bang. Quarks, elementary particles ordinarily contained within protons and neutrons, were free to move about at these temperatures. These quarks were combined with gluons, carriers of the basic force known as the strong force, in a primordial that pervaded the whole universe. In particle accelerators on Earth, scientists have replicated these circumstances in both terrestrial atom smashers and the early cosmos. The challenging to achieve condition only lasted for a few fractions of a second. The early epoch, the subsequent period of time, beginning perhaps in the neighborhood of a few thousandths of a second following the Big Bang, was a period of intense activity. The universe chilled as it expanded, creating an environment conducive to the merger of quarks into protons and neutrons. The cosmic neutrino background, which has not yet been detected by scientists, was created 1 second after the Big Bang when the density of the cosmos decreased sufficiently for neutrinos to sail across space without interacting with anything. The first atoms, protons, and neutrons fused together during the first 3 minutes of the universe's existence, creating the isotope of hydrogen known as deuterium, along with helium and a trace quantity of the next lightest element, lithium. Yet this procedure ceased as the temperature dropped. As temperature settled down 380,000 years after the Big Bang, hydrogen and helium atoms could join with free electrons to form the first neutral atoms. The cosmic microwave background is a remnant of this, not a location in space. From when all else unfolded to be more precise, it's the first second of time, the point in history from which all other seconds have been measured. The Big Bang, despite its common name, was not an explosion, but rather a time when the universe was incredibly hot and dense before space began to expand outward in all directions simultaneously. The Big Bang scenario suggests that the universe was an infinitesimally small point of infinite density. However, this is merely a convenient way of expressing that we don't know for sure what happened at that time. We now understand the cosmos to break down at the Big Bang because mathematical infinities don't make sense in physics equations. Cosmic inflation era. The next cosmic phenomenon was to rapidly expand in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but it has gained favor among cosmologists as a possible explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014. Nevertheless, further investigation revealed that the true culprit was nothing more than interplanetary dust causing interference. Quark gluon plasma. The temperature of the early cosmos was between 7 trillion and 10 trillion degrees Fahrenheit or 4 trillion and 6 trillion degrees Celsius, just a few milliseconds after the Big Bang. Quarks, elementary particles ordinarily contained within protons and neutrons, were free to move about at these temperatures. These quarks were combined with gluons, carriers of the basic force known as the strong force, in a primordial that pervaded the whole universe. In particle accelerators on Earth, scientists have replicated these circumstances in both terrestrial atom smashers and the early cosmos. The challenging to achieve condition only lasted for a few fractions of a second. The early epoch, the subsequent period of time beginning perhaps in the neighborhood of a few thousandths of a second following the Big Bang, was a period of intense activity. The universe chilled as it expanded, creating an environment conducive to the merger of quarks into protons and neutrons. The cosmic neutrino background, which has not yet been detected by scientists, was created 1 second after the Big Bang when the density of the cosmos decreased sufficiently for neutrinos to sail across space without interacting with anything. The first atoms, protons, and neutrons fused together during the first 3 minutes of the universe's existence, creating the isotope of hydrogen known as deuterium, along with helium and a trace quantity of the next lightest element, lithium. Yet this procedure ceased as the temperature dropped. As temperature settled down 380,000 years after the Big Bang, hydrogen and helium atoms could join with free electrons. Microwave background is a remnant of this. Distances. Thanks for watching, and don't forget to hit the like button, subscribe, and turn on notifications for more content like this in the future. The universe is a vast and mysterious place, filled with countless wonders and secrets waiting to be discovered. Among the many mysteries of the cosmos, one of the most fascinating and profound is the age of the universe itself. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. Scientists have spent decades studying the universe using a variety of tools and techniques to unravel the mysteries of our cosmic past. Through their efforts, they have determined that the universe is estimated to be around 13.8 billion years old. The search for the age of the universe began in the early 20th century when astronomers first realized that our universe was expanding. The concept of an expanding universe was first proposed by Belgian astronomer Georges Lemaitre in 1927, but it wasn't until the work of American astronomer Edwin Hubble in the 1920s and 1930s that the idea was widely accepted. Hubble's groundbreaking observations of distant galaxies revealed that they were moving away from us at great speeds, and that the farther away a galaxy was, the faster it was moving. This relationship, known as Hubble's law, suggested that the universe was not static, but was instead expanding. If the universe was expanding, then it must have been smaller in the past, and this realization led scientists to wonder just how old the universe was. The first attempts to estimate the age of the universe were based on models of stellar evolution. Scientists knew that stars undergo a predictable sequence of changes as they age, and they thought that by studying the properties of stars in our own galaxy, they could determine the age of the universe. However, these early estimates were plagued by uncertainties in our understanding of stellar evolution, and they varied widely from a few million years to several billion years. It wasn't until the 1960s that a more accurate method for determining the age of the universe was discovered. In 1964, two astronomers named Arno Penzias and Robert Wilson discovered a faint background radiation that was present in all directions of the sky. This radiation, known as the cosmic microwave background, CMB, is thought to be the leftover radiation from the Big Bang, the event that marked the birth of the universe. The discovery of the CMB was a major breakthrough in our understanding of the universe, and it provided scientists with a powerful tool for estimating the age of the universe. By studying the properties of the CMB, scientists could infer important details about the early universe, such as its temperature and composition. This information, in turn, could be used to estimate the age of the universe. Over the next few decades, scientists refined their measurements of the CMB and improved their understanding of the early universe. They also developed more sophisticated models of cosmic evolution, which took into account the effects of dark matter and dark energy, two mysterious substances that make up the majority of the universe. By combining these observations and models, scientists arrived at an estimate for the age of the universe, 13.8 billion years. This estimate has been confirmed by a variety of independent measurements, including observations of distant supernovae and the large-scale structure of the universe. The age of the universe is one of the most well-established facts in cosmology, and it has profound implications for our understanding of the cosmos. The age of the universe tells us that our universe has a long and fascinating history, stretching back billions of years to a time when the universe was just a tiny, hot, and dense singularity. It tells us that the stars and galaxies we see today are the result of billions of years of cosmic evolution, driven by the forces of gravity and the interplay between matter and energy. 13.8 billion years old. Why is it still expanding at an accelerating rate? What is the nature of dark matter and dark energy, and how do they shape the evolution of the universe? How did the first stars and galaxies form, and what was the nature of the universe in its earliest moments? These are just a few of the many questions that cosmologists are working to answer. The age of the universe provides a crucial piece of information in the quest to understand the cosmos, but it is just one piece of a much larger puzzle. One of the most fascinating aspects of the age of the universe is how it connects to the fundamental nature of space and time. According to Einstein's theory of general relativity, space and time are intertwined, forming a four-dimensional fabric and distorted by the presence of matter and energy, leading to phenomena like gravitational waves and black holes. The age of the universe tells us that space-time has been evolving for billions of years, stretching and warping in response to the forces of the cosmos. It tells us that the very fabric of the universe has a history, and that the structures we see today are the result of an intricate interplay between space-time, matter, and energy. While the universe is expanding at an accelerating rate today, it is still unclear what the ultimate fate of the universe will be. Some theories suggest that the universe will continue to expand forever, eventually becoming a cold and dark place devoid of stars and galaxies. Other theories suggest that the universe will eventually collapse in on itself, leading to another Big Bang and the birth of a new universe. Whatever the ultimate fate of the universe may be, the age of the universe tells us that we are living in a remarkable moment in cosmic history. We have the opportunity to study the universe at a time when it is still evolving and changing, when stars are still being born, and galaxies are still colliding and merging. By studying the universe and its evolution, we can gain insights into the fundamental nature of the cosmos and our place within it. The age of the universe also provides us with insights into the likelihood of intelligent civilizations existing elsewhere in the cosmos. If life is a relatively common occurrence in the universe, and if the conditions for the development of intelligent life are present on other planets, then there may be many civilizations out there that are much older and more advanced than our own. Moreover, the age of the universe has implications for our search for extraterrestrial life. By studying the conditions that led to the emergence of life on Earth, and by exploring the diversity of life forms on our planet, we can gain insights into the types of environments and conditions that might be conducive to the emergence of life elsewhere in the universe. Some theories suggest that the universe is just one of many in a multiverse, a vast and complex network of parallel universes with their own unique properties and histories. The age of the universe tells us that if a multiverse does exist, then there has been ample time for the emergence of many different universes, each with its own unique history and destiny. Finally, the age of the universe reminds us of the incredible beauty and wonder of the cosmos. From the cosmic microwave background radiation left over from the Big Bang to the intricate dance of stars and galaxies across the night sky, the universe is a rich and complex tapestry of phenomena that is both awe-inspiring and humbling. In conclusion, the age of the universe is a remarkable fact that has profound implications for our understanding of the cosmos and our place within it. It tells us about the origins and evolution of the universe, the potential for extraterrestrial life, the nature of reality itself, and the beauty and wonder of the cosmos. As we continue to explore the mysteries of the universe, the age of the universe will remain a key piece of information guiding us in our quest to understand the cosmos and our place within it. We inhabit a galaxy known as the Milky Way, which contains hundreds of billions of stars. How did we arrive at this point, and what is our future? These concerns involve galaxies in every aspect. The known universe contains 200 billion galaxies, each of which is unique, immense, and dynamic. Where do galaxies come from? How do they work? What is their future, and how will they die? If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. This is the Milky Way, our galaxy, approximately 12 billion years old. The galaxy is a vast disk with enormous spiral arms and a central nucleus. It is only one of countless galaxies in the universe. Galaxies are massive assemblages of stars. First and foremost, a typical galaxy could contain 100 billion stars. They are actually stellar nurseries, the locations where stars are formed and perish. The stars in a galaxy are formed in nebulas, which are concentrations of dust and gas. Our galaxy contains billions of stars, many of which have planets and moons orbiting them. But for a very long time, we knew very little about galaxies. A century ago, we believed that the Milky Way was the only galaxy in the universe. In 1924, astronomer Edwin Hubble altered the entire situation. Hubble observed the universe using the most sophisticated telescope available at the time, the 100-inch hooker on Mount Wilson. He saw hazy masses of light in the darkness of the night sky. He realized they were not even separate stars. They were entire star-filled cities, constellations far beyond the Milky Way. The astronomers received an existential jolt. We went from the Milky Way galaxy being the only galaxy in the universe. In a single year, Hubble made one of the finest discoveries in the history of astronomy when he discovered that the universe contains a large number of galaxies rather than just one. The Whirlpool Galaxy, comprising over 160 million stars and characterized by two enormous spiral arms, and the Sombrero Galaxy, with a massive bright core surrounded by a cloud of gas and dust, are just two examples of these captivating celestial formations. Galaxies, which resemble enormous pinwheels as they spin across space, serve as the fundamental building blocks of the cosmos. The vast scale of galaxies is emphasized by the fact that while our galaxy seems enormous from Earth, it is relatively small when compared to other galaxies. The origin of galaxies is a key mystery in astrophysics, dating back approximately 13.7 billion years to the Big Bang. Galaxies must have formed from the very early universe due to the clumping together of their masses from gravitational forces. Thanks to the Hubble Space Telescope, we can witness the early universe when galaxies were just beginning to form, a mere 200 million years after the first stars emerged. The Hubble Deep Field captures barely visible blotches representing the oldest galaxies, which began to take shape around 1 billion years after the Big Bang. However, to travel much further back in time and trace the evolution of galaxy formation, a larger telescope, not viable for space travel, is necessary. By observing the formation and evolution of galaxies and galaxy clusters, astronomers are getting closer to answering the question of what young galaxies look like. Ultimately, galaxies evolved from clusters of stars to the complex web of systems we see today, providing a glimpse into the incredible structures and mysteries of the universe. Originating as star clusters, evolving into galaxies, forming clusters of galaxies, and ultimately coalescing into superclusters of galaxies, there was a lot of stardust, gas, and clumpy structures in the early galaxies. However, modern galaxies seem organized and tidy. When and how can tangled clusters of galaxies become neatly organized spirals and pinwheels? Gravity is the explanation. Galaxies are molded by gravity, and its effect determines their fate. At the center of most galaxies lies an unfathomably strong and destructive gravitational source, and our home Milky Way has one hidden at its core. Over 12 billion years have passed since galaxies first appeared. These stellar conglomerations may take many forms, from spirals to giant spheres of stars. However, there is still a great deal we don't understand about galaxies. How did galaxies evolve into their present forms? Did spiral galaxies always have to be spirals? The answer is almost certainly no. Young galaxies are a mix of stars, gas, and dust. They are untidy and chaotic. They begin as chaotic formations like the Whirlpool galaxy, then develop into more orderly forms over billions of years. The Milky Way wasn't born from a single galaxy, but from a cluster of several. Our Milky Way originated as a collection of disparate formations, objects of varying sizes and shapes that gradually merged to become the galaxy we see today. Gravity is what binds the various components together. Over time, it gradually draws stars closer. They pick up speed and flatten out into a disk shape. Massive spiral arms gather stardust and gas. This process was carried out countless times during the course of the cosmos. While visually distinct, these galaxies share the fact that they all seem to circle the same central object. For a long time, researchers pondered what might possibly alter a galaxy's behavior, and they found out. A black hole, and not just any kind of black hole, but a supermassive black hole. The discovery of extreme amounts of radiation coming from the centers of certain galaxies was the first indication of supermassive black holes. Black holes in these galaxies are consuming their surroundings, much like a giant Thanksgiving feast. Sometimes, black holes consume their food so rapidly that they spew it out into space as a beam of pure energy. They refer to it as a quasar. The presence of a quasar indicates the presence of a supermassive black hole at the center of the galaxy. However, what about the Milky Way? There's no quasar here. Does it rule out the existence of a supermassive black hole? Observing the motion of the stars is the key to finding the supermassive black hole. The sun, the stars also move to the pull of gravity. What we discovered was a bizarre and violent environment at the center of our galaxy. Everything is more extreme. Things move very quickly. The stars will be passing one another at high speeds. It is unlike any other place in the universe. The photographs of the stars in orbit showed a remarkable phenomenon. They had to have been traveling at 1,000,000 miles an hour or more. Only a gigantic black hole has the energy to toss large stars. Around like that, this curvature was the conclusive evidence for a supermassive black hole at the heart of our galaxy, as it is the black hole's gravity that drives the orbits of these stars. A massive black hole, measuring 15 million miles wide, sits at the heart of our Milky Way galaxy. So is there any danger to Earth? We are in absolutely no danger of being sucked into our supermassive black hole. It's simply too far away. In reality, the distance between Earth and the supermassive black hole in the heart of the Milky Way galaxy is 25,000 light years. That's many trillions of miles. For the time being, Earth is secure. Although supermassive black holes are the source of enormous quantities of gravity, they are not strong enough to bind galaxies together. In reality, the rules of physics dictate that galaxies should accelerate away from one another. So, what's stopping them? Because there's something stronger than a gigantic black hole waiting to be discovered. It is invisible and very difficult to detect. It's called dark matter, and it's everywhere. Supermassive black holes discovered by astronomers are found in the centers of galaxies and are responsible for the rapid movement of stars in their vicinity. However, they are insufficient to hold together all of the stars in a vast galaxy. So, what does hold them together? It was a mystery until a maverick scientist proposed that something unknown was at action. Fritz Zwicky, a Swiss astronomer, pondered in the 1930s why galaxies clustered together. He reasoned that because they weren't producing enough gravity, they should be flying apart. However, the force of our own gravity was insufficient. Therefore, he deduced that it must be something that had never been discovered before, something that had never even been considered, and he called it dark matter. Fritz Zwicky was decades ahead of his time, and that's why he graded on the astronomical community. This is a brilliant idea, but he was correct. Individual galaxies are also held together by the mysterious substance that Zwicky dubbed dark matter. Galaxies rely on dark matter as a kind of protective framework that keeps them from collapsing and moving about. Now, scientists have discovered that dark matter does more than just bind galaxies together. It may have also triggered their evolution. Scientists believe that after the Big Bang, dark matter started to cluster, and these dark matter clumps evolved into the galaxy nucleus. However, the nature of dark matter is still a mystery to physicists. Weird things happen with dark matter. Since we don't know what it is, obviously, it's not constructed from the same substance that humans are. You can't push against it. You can't feel it. However, it is likely everywhere. It's a ghost-like material that will pass right through you as if you didn't exist at all. Although our understanding of dark matter is limited, it seems to be abundant across the cosmos. That means there must be at least 6 times as much dark matter as regular matter, what humans are comprised of. In the cosmos and the way the cosmos seems to function depends on it. Observation of its effects on light have led to its recent indirect detection in deep space through a process known as gravitational lensing. It warps the light. The existence of dark matter may be tested using gravitational lensing. As a ray of light from a distant galaxy travels towards us, its course will be bent around a huge collection of dark matter due to the latter's greater gravitational attraction. Some distant galaxies indeed seem stretched and warped when seen via the Hubble telescope. The picture distortion is due to the presence of dark matter. We can determine the density of dark matter by carefully examining the forms and degrees of distortion of these galaxies.
Dark matter rules
Now more
the
than ever,
cosmos.
making galaxies form and preventing their collapse despite being invisible and undetectable. Galaxies are not isolated. They exist in clusters and superclusters, shaping the cosmos. Our Milky Way is part of a smaller group of about 30 galaxies and itself resides within the larger Virgo supercluster. Galaxies, vast star empires, constantly evolve and move, sometimes colliding and merging over millions of years. Notably, the Milky Way is on a collision course with the Andromeda Galaxy, which will lead to their merger in about 5 to 6 billion years. The collision will be spectacular, causing the birth of a new galaxy. However, this age of galactic collisions will pass, giving way to an even more destructive force known as dark energy. Unlike dark matter, dark energy pushes galaxies apart, accelerating the expansion of the universe. In a far future, galaxies will eventually die off due to dark energy, leading to their disappearance over 1 trillion years. Despite this, the present conditions in the cosmos remain conducive to life. The formation of galaxies in the right regions has created favorable circumstances for life to exist. The proximity of our solar system to the core of the Milky Way could have rendered it hazardous for life as we know it. Therefore, the continued existence of galaxies is vital for life as we understand it. It's impossible for life to continue in any form too far away from the center. Out there, there aren't as many stars, and we might not exist at all. Therefore, in a sense, we're in the Goldilocks zone of the galaxy, neither too close nor too far away, but just right. There may be millions of stars in the cosmic Goldilocks zone, where conditions are just suitable for life. Furthermore, if our galaxy can support life, then other galaxies should be able to do so as well. The cosmos is very large, and the really incredible part is that we continue to learn new things about it. Every time we believe we've figured out a solution to an issue, we uncover that it's really part of an even greater one. That's awesome. Our Milky Way galaxy and the galaxies beyond it are rife with mysteries and unanswered questions. Who would have guessed 20 years ago that we would be able to identify the black hole at the center of the galaxy? Who would have predicted 20 years ago that the astronomical community would accept the existence of dark matter and dark energy? We should be astonished to be alive at this particular moment in cosmic history, on this particular planet, on the fringes of this particular galaxy, with the ability to ponder questions and seek answers across the whole cosmos. Galaxies are born, they evolve, they collide, and they die. The Milky Way is a fortunate home for intelligent life. Our fate is intertwined with that of every galaxy. Ultimately, our fate rests in their hands since they are the ones who created us and are shaping our identities. We used to only know about the planets that circled around our sun, but now we know that there are rocky worlds and huge gas clouds that circle other stars. They have a great story to tell. The early history of these planets would have been very violent. Planets are made the same way everywhere. They come from the dust and other things that are left over after stars are born. So, what makes them so different? As it turns out, the universe is full of galaxies, gas clouds, stars, and planets. There are 8 worlds in our sun system, but now we know that they are just a small part of the huge family of planets in the sky. It's a very important moment in the history of science to be sure that there are other systems of planets out there. In our Milky Way galaxy, which has 200 billion stars, there are probably dozens of planets. NASA sent the Kepler Space Telescope into space in 2009 on a 6-year mission to find new planets that orbit other stars. So far, they have found more than 400. Some are huge spinning balls of gas that are 5 times as big as Jupiter, and others are huge rocky worlds many times larger than Earth. Some planets follow wild erratic orbits, so close to a star that they're burning up. One thing is clear, no 2 planets are the same. Each one is unique. However, most of these new worlds are very far away and hard to study. Most of what we know about how planets work come in 2 main types. There are 4 rocky planets in the inner solar system: Mercury, Venus, Earth, and Mars. In the outer solar system, there are 4 giant gas planets: Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the other 7. When our solar system was born 4.6 billion years ago, they started to develop their own personalities. When the sun ignited, it released a massive cloud of gas and dust into space. All 8 planets, including the metal planets closer to the sun and the gas planets farther away, came from this cloud of space debris. All of the worlds in our solar system are made of the same materials. They're made from the same cloud of gas and dust, but they formed under very different conditions. Some of them formed close to the sun where it was much hotter, and some formed far away where it was much colder. And since the situations were so different, the things that came out of them were all different. So at the beginning of the solar system, there was a pretty even mix of silicates, water vapor, hydrogen, methane, and others. These elements in the dust cloud are like ingredients in a cake. They cook in different ways based on how the environment around them is. Ingredients are mixed and how hot the oven is, and you mix the ingredients just like you did with the cake. Then you put it in the oven and bake it, and it would change. So basically, this is what happened in the solar system. Overall, the planet cooks in a slightly different way depending on how close it is to the sun. Near the sun, where it is hot, gases are burned off and water is boiled away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the sun. As a planet moves farther away from the sun, It cooks in a different way. But what kind of planets will form depends on what's in the cloud. Based on what kind of cloud a solar system forms in, it might not have any rocky planets because it didn't have enough materials to make something like Earth. Instead, it might have more gas giants and none at all. If you want planets that are made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the things in it that have a high boiling point start to condense out as solids, and these very small mineral grains can start to form. These tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust molecule and another dust molecule, they would basically hit each other and make one slightly bigger dust molecule, and they keep getting more and more. This process is called accretion. As these things got bigger, they became basically rocks. Then rocks slam into other rocks and form boulders. Boulders smash together to form bigger boulders. At some point, you'll have something big enough that its weight is strong enough to start pulling things towards it. So instead of just crashing into things and getting bigger that way, it was actively pulling things in. At first, there were a lot of young planets in our own solar system, maybe 100. Most of them didn't make it. If you go to the asteroid belt and look at the asteroid 4 Vesta, you can get a good idea of how big a hard planet has to be before it can pull itself into a sphere shape. Vesta is only 329 m across, which isn't quite big enough to be a sphere. To become round, a growing planet needs to be 500 m across, then it has enough gravity to crush it into a sphere. Any smaller, and it stays in an irregular shape. Every time a round baby planet crashes into something, it makes it hotter and hotter until it starts to melt. Gravity is now starting to sort the heavy things from the lighter ones. Lighter things tend to float up and form a crusty layer, while heavy things like most metals fall down and form a much denser core at the planet's center. Finally, the young planets are starting to look like planets, but now they have to make it through a time of violence and destruction, a cruel time that will decide which planets will live and which will die. After the sun was made, all 8 of our planets came from the same cloud of dust and gas, but they turned out to be very different. There was no real plan for how each of the new planets should be made. They did follow the rules of physics and chemistry, but most of what happened was just a matter of luck. About 4.5 billion years ago, our sun was surrounded by about 100 young planets. It turned into a demolition derby. Planet hit planet, most were wiped out. The early history of these planets would have been very, very violent, with many of these collisions happening in the last stages. Things ran into each other. Some of the planetesimals started to grow at the expense of the others, and these things that would eventually become planets grew and grew. As they got bigger, they sucked up all the smaller planetesimals around them, which caused a lot of space debris to hit the surface of the protoplanet. After it was over, there were only 4 different rocky planets left. Because of the things that happened to each planet in the past, they are all so different from each other. Mars is a frozen wasteland, Earth flows with liquid water, Venus is a place full of volcanoes, and Mercury is small, empty, and very hot. Because of a huge crash, Mercury, for example, has a very thin crust and is very dense. So it could have been a bigger planet in the past. Then something hit it at an angle, which tore. The young Earth was hit hard at the end of its development, leading to the tearing of its mantle and the formation of the Moon from the sent pieces. Similar collisions also seem to have affected Mars, as evidenced by the different thickness of the crust in the planet's northern and southern hemispheres. These collisions not only reduced the number of surviving young planets, but also supplied additional materials to those that persisted. Near the Sun, the rocky planets, consisting of a solid core of hot iron, liquid iron layer, and molten rock shell, were nearly completed. Each of these planets, despite being made from the same basic materials, emerged with distinct sizes and destinies. While space may appear empty, it is filled with matter from the Sun, including the solar wind, which consists of charged particles. Astronauts can perceive the solar wind as flashes of light when they close their eyes, making protection from radiation crucial in space travel. Fortunately, on Earth, the planet's magnetic field shields us from the solar wind, derived from the Earth's hot liquid metal flowing around the solid core and converting its energy into a magnetic field. This field repels the solar wind and protects the planet's atmosphere and surface. In the absence of a protective magnetic field, like on Mars, a planet can lose its atmosphere and water to the solar wind, rendering it arid and lifeless. NASA's Mars rovers, Spirit and Opportunity, confirmed that Mars is currently a dry, inhospitable desert. However, evidence suggests that Mars had water below the surface at one point, with signs of water flowing over the surface and evaporating away. The presence of volcanoes in Mars' past indicates a hot interior and the likely existence of a magnetic field. However, Mars' smaller size caused it to lose heat more rapidly, and its core may have frozen, halting the magnetic field's convection. Ultimately, these factors have contributed to the stark differences between Earth, a vibrant and water-rich planet, and Mars, a cold and dry wasteland. Mars lost its magnetic field, causing the solar wind to strip away its atmosphere and water, transforming it into a cold, desolate planet. Close to the Sun, rocky planets like Mars, Earth, Venus, and Mercury formed, while farther out, gas giants, Jupiter, Saturn, Uranus, and Neptune, emerged. The gas giants likely formed from frozen gas and dust, leading to the growth of massive cores, drawing in surrounding gases to create thick atmospheres tens of thousands of miles deep. These planets also acquired numerous moons and distinctive rings, with Saturn's being the most notable. The gas giants harbor mysteries deep beneath their atmospheres, with extreme conditions challenging our understanding of natural laws. Little is known about their interiors, including Jupiter's violent storms and high-speed gas movements. Despite sending probes like Galileo to gather data, the inner workings of gas giants remain largely elusive, with immense pressure hindering Jupiter, have extreme temperatures and high atmospheric pressure, making exploration challenging. Jupiter's strong magnetic field also influences its moons like Io, leading to intense radiation belts and auroras. The formation of gas giants' magnetic fields remains a mystery, as they lack Earth's hot liquid metal core. Whether Jupiter has a solid core or remains liquid deep within is unknown, as existing probes can't reach its center. Water plays a crucial role in planet formation and evolution. Earth acquired water from watery asteroids and comets. The right amount of water on Earth allowed for the evolution of life, showcasing the importance of water in planetary development. The abundance of water in the universe suggests its widespread presence, but finding planets with liquid water remains a challenge, despite the discovery of over 400 new planets. Scientists are yet to find a planet similar to Earth in size, mass, and chemical makeup, but with billions of planets out there, the search continues. Volcanoes play a vital role in planetary exploration, impacting climate and potentially influencing the existence of life. Venus, once similar to Earth, now exhibits a fiery, greenhouse-like environment due to its volcanoes and dense carbon dioxide atmosphere. Additionally, the discovery of active volcanoes on Jupiter's moon Io, which is smaller than Earth's moon, has defied initial assumptions about its geological activity. Jupiter's gravitational force causes solid rock tides on Io, leading to extreme volcanic activity, with eruptions yielding plumes that extend into space. This unique phenomenon challenges our understanding of how such a small moon can exhibit such intense volcanic activity. Pressure. Wherever there are weak spots in the crust, lava erupts. Volcanism is therefore planet-scale. In contrast to Earth, where certain portions are active around the plates or in weak areas, this is an entire moon that's one active hotspot. Io is the most volcanism active planet in the solar system. As a result of the immense power of gravity, volcanic activity on Io has taught us something new. It taught us that internal energy sources can drive volcanism in a manner distinct from that on Earth. Io is a lava world that is extremely hot and violent. It is difficult to conceive of anything surviving there. We have discovered strange eruptions on numerous planets and moons, but so far, the only world where volcanoes are linked to life is ours, or so we thought. This is Europa. It orbits Jupiter at a distance of nearly 500 million miles from the Sun and is a 2,000 meters wide sphere of ice. From afar, its surface appears to be polished. Up close, it's a different story. Europa is pummeled by Jupiter's immense gravity, just like its companion Io. The surface rises and bends, forming ridges and deep fissures. When we first obtained close-up images of Jupiter's moon Europa, they seemed vaguely familiar. And it turns out that they resemble Arctic ice flows. And it turns out they are the same. A global liquid ocean lies beneath Europa's several-mile-thick icy crust. Magnetic measurements indicate Europa's ocean is an astounding 60 miles deep. The gravitational impact of Jupiter heating the rocky interior and melts the ice above, as the core is stretched by tides and heated, possibly melting. It is not preposterous to believe that there is a boundary between a hot core and a liquid water ocean. Underwater eruptions on Earth are surrounded by life. The same may occur on Europa. Here the darkness is complete, the pressure a crushing 2,000 Earth atmospheres, a harsh environment, but perhaps a CR for life. If there is evidence of life on Earth, why not Europa? An energy source, volcanic activity, a universal solvent, liquid water, and a complex hydrocarbon chemistry are all present. Life would be difficult, but not impossible on Europa. There is life at every extreme on Earth, including searing heat, crushing pressure, and absolute darkness. Life on Europa may resemble our own in unanticipated ways. If life exists beneath Europa's ice, it would be aquatic, but without eyes because there is no significant light. Organisms that essentially feed off the energy of the volcano would most likely utilize sonar to make sense of their surroundings. Volcanoes on Europa could be the genesis of new life. It is even conceivable that Europa is typical, that this is the norm for planets with life. Earth may represent an exception. Consider that Europa could serve as a model for the billions of moons in the universe with liquid oceans. So all of a sudden, our horizons have expanded several billion times by looking at the moons of Jupiter. Our solar system is home to more than 170 moons. Multiply this by the size of the universe, and that's a lot of potential habitats for life. Only liquid water and a source of energy are required. Potentially both are provided by volcanoes, and they are ubiquitous.